Understanding vast forces in space and how they affect life here on Earth requires comprehending what's going on out there. NASA is planning to launch 4 identical spacecraft that will orbit the Earth through the dynamic magnetic system surrounding our planet, studying a little understood phenomenon called magnetic reconnection. Magnetic reconnection is unique to plasma, that is, the mix of positively and negatively charged particles that make up stars, fill space, and account for an estimated 99% of the observable universe. On October 28, 2003, and again the following day, massive solar flares erupted on the Sun, sending X-rays zooming through the solar system. Along with the flares, the Sun expelled giant clouds of solar material called coronal mass ejections, or CMEs. The CMEs slammed into Earth's magnetic field and pushed material and energy in toward Earth. This created what's called a geomagnetic storm that can interrupt the work of satellites we have come to depend on.
So you can think of it as kind of like a magnetic explosion. And the reason this is important is because these explosions drive a lot of the weather patterns that we see in the magnetosphere, and so what space scientists like to refer to as space weather.
NASA's Magnetospheric Multiscale Satellites, or MMS, should help scientists understand and better predict space weather patterns.
The MMS mission is a mission consisting of 4 spacecraft which will fly in close constellation to measure a process called magnetic reconnection. We need to measure reconnection in more than one location. We need to measure it in basically how it varies in space, how it varies in all 3 spatial dimensions.
Scientists want to know exactly what conditions, what tipping points, trigger magnetic reconnection events. Much of what we currently know about the small-scale physics of magnetic reconnection comes from theoretical studies, computer models, and laboratory experiments. Better understanding requires observing magnetic reconnection up close. So MMS will make its measurements in Earth's magnetosphere an ideal natural laboratory in which reconnection can be observed under a wide range of conditions. But before MMS and its science team can begin their studies, the satellites must be prepared for launch into orbit.
Once they arrived, several things had to be done. They had to be fueled, they had to be processed down here, and remember there's 4 spacecraft, so it took 4 times the effort.
NASA's Launch Services Program has extensive experience preparing multiple probes for liftoff on a single rocket. In September 2011, the GRAIL mission sent 2 spacecraft to the Moon. More recently, the twin radiation belt storm probe satellites were launched in 2013. But with MMS, there are 4. Omar Baez is the MMS launch director for the Launch Services Program at NASA's Kennedy Space Center in Florida.
Yeah, it would be simpler to do 1 spacecraft, but we're here to do the difficult things, and that's why this business is so interesting.
As NASA's launch manager, Baez oversees integration of the satellites with a familiar rocket, the Atlas V.
The Launch Services Program contracts the launch service to United Launch Alliance, and this has been a team that has worked together since the inception of the Launch Services Program here in 1998. We work very closely with ULA from the very design of the mission, or from the very contracting of the mission, through the design, through the integration, and finally through the operations and buildup of the launch vehicle and final launch.
Once in orbit, the next challenge is deploying all 4 MMS satellites.
To get them in the right orbit and the right place is a complicated flight design challenge that our team has had. Amazing amount of maneuvers we have to do with the Centaur upper stage to make sure we release all 4 of the spacecraft at the right timing. It's a 5-minute intervals between release. So if you can imagine, that first one pops off, and then the second one 5 minutes later, third one another 5 minutes, and so on.
After months of testing, the quartet of MMS satellites will be ready to go to work.
Once they're commissioned after that 6-month time frame, they formation fly in a tetrahedron formation, and they'll go around the Earth to pick up this reconnection event that we find on both sides of the Earth, where the magnetosphere of the sun's magnetic field and the Earth's magnetic field meet on the sun side, and then on the tail side of the magnetotail of the Earth on the dark side of the Earth.
The spacecraft fly through such a site. They will measure the magnetic and electric fields present, as well as the movement of particles.
We need to understand both of those if we want to understand how the magnetosphere works, and we believe that both of those scenarios are also very important for other applications, such as on the Sun, in the solar wind, in planetary magnetospheres, and in many astrophysical objects, as well as in the laboratory.
During its first phase, MMS satellites will travel through reconnection sites on the Sun side of Earth. During the second phase of its mission, MMS will observe reconnection on the night side, where that connected field flows around both sides of our planet to a second reconnection point.
On the day side, basically you have a situation where the solar wind is just constantly running into Earth's magnetic field. And this is really great for MMS because we know that at some point MMS is going to encounter this region, and our hope is that since this process is always happening, we're going to get lucky and actually fly right through the magnetic explosion as it's happening. Now on the night side, the situation is a little bit different. So what happens is you have a more gradual buildup of magnetic energy in the tail, and these reconnection processes, these magnetic explosions, can just sort of pop off randomly. We don't really know when it's going to happen or where it's going to happen.
During the MMS mission, scientists will have their first chance to watch magnetic reconnection right as it's occurring. By focusing on the small-scale process, scientists may be able to open the door to understanding what happens on larger scales throughout the universe. Of course, it also will teach us more about giant geomagnetic storms, thus helping us safeguard our home planet.
We hope that it's going to allow us to improve our models so that we can put the right physics in it and actually make predictions about where and when reconnection is going to happen, and this will help us make our space weather models more predictively powerful.